Hello everyone, I am Yogesh Deshpande. Along with me, my team members would like to present application of computational technique in experimental study of abrasive water jet machining of aircraft materials. These are the contents of this presentation. Machining is the important activity because the machining activity contributing to the growth of global economy, and that's why in this slide here the various factors are considered for improving the machining performance and to optimize the machining conditions. By looking the conventional and unconventional machinings and some drawbacks of unconventional machinings like the poor tool life, poor surface finish, then creating the pollution during and after the machining process, and therefore the conventional machines are not suitable to cut the difficult or hard materials just like the superalloys based on the cost factor and quality factor. And that's why here the need of unconventional machining is arises. So out of the various unconventional machining tools, here the abrasive water jet machining technology is selected because it has the wide usage in automobile and aerospace industries, which provides the good quality of the product, high machining versatility, and many more applications. Here, the schematic arrangement of abrasive water jet machining (AWGM) is presented here. So, the focusing tube and the mixing chamber together mix the injected abrasive, and then the high pressure water with the abrasive particles impinging on the workpiece material, and the workpiece is cutted as per the desirability. The complex shapes can be marked using AWGM, and that's why here the AWGM used in various industrial sectors. By looking the difficult to cut materials just like the nickel and titanium alloys. So here the super alloys showing the three important components: nickel base, iron base, and cobalt base. In this research work, Inconel 718 is used for the machining purpose because here it is used in various industrial sector and specifically used in the hot section of the jet engine. Here various advantages of the Inconel 718 because of its the abrasive in nature, low thermal conductivity, but at the same time it poses the difficulties in machining which resulted low to life and surface finish. And that's why here the machining of such type of the aircraft material is the challenging job for the shop floor industries. These are some key points are recorded after literature review and industrial survey. Based on these points, here the objectives are framed. Here, first one is the experimentation, then identification of significant and insignificant AWGM parameters, modeling, and to identify the optimum points to enhance the machinability of Inconel 718. So this is the AWGM used in this watch. So these are the some specification is highlighted here. Workpiece material, as we know, the nickel-based superalloy is selected, and this slide shows the microstructure details along with the EDX plot and the properties of Inconel 718. The workpiece of Inconel 718 along with the machine component is presented here. While planning the experimentation, here the RSM is the most useful technique as the RSM is categorized in two ways: box Behenken and central composite designed. So here CCD of RSM is used because it provides the 5 labels of the factors. So these are the labels are presented here with abrasive flow rate, standoff distance, and travel speed as the input process parameters. The AWGM unit with the highlights is presented here. This is the video showing the how pressurized water with abrasive particle cuts the material. After conducting the experimentation using the response surface methodology, design methodology, here the surface quality of the machine part is measured using the surface roughness tester. Also, the curve taper angle is measured with the relationship of the upper curve width minus lower curve width by 2t. So, the cone angle or curve taper angle can be calculated. And the value of surface roughness and theta are tabulated against the input parameters for the 20 experimentation. While looking the various modeling techniques, here the researchers use the response surface methodology for machining of the various metals. But such methodology is rarely used in machining of superalloys, and that's why RSM is selected here. RSM shows this is the standard mathematical model, and for the simplicity and providing the good relationship among the input and response variables, the RSM is more applicable for such cases according to the Montgomery. ANOVA analysis is also carried out, and based on the ANOVA analysis, here the surface roughness is analyzed, and here it is noticed that travel speed is the most significant factor, followed by abrasive flow rate and standoff distance. Here the main effect plots and 3D plots are presented. Here see, by increasing the abrasive flow rate, surface roughness value is decreases, but by increasing the standoff distance and travel speed, the value of RA is increases. By looking some 3D surface plot, here the high peak point indicated by red color shows the high value of surface roughness at minimum flow rate and maximum standoff distance. In second picture, it is noticed that the low value of surface roughness achieved at the high flow rate and low travel speed. In this way, the various plots are drawn and studied here. Secondly, the analysis of cone angle, curve taper angle, theta is analyzed. Here also, travel speed is the most significant factor. And by increasing the flow rate, the theta value decreases. Similarly, by increasing standoff distance and travel speed, theta value increases. While looking the interaction plot, it is noticed that at high value of theta means the low flow rate and high standoff distance. While looking the second diagram, bottom point, here the value of theta is very low, means that it achieved at the high flow rate and low travel speed. Similarly, here also the value of theta is low, means here the standoff distance is low and travel speed is low. In this way, these points and interaction plots can be studied. At last, the multi-objective optimization is performed using the RSM with the aim of minimization of surface roughness and cone angle theta. Here, the desirability approach is used for the minimization of RA and theta, and the plot is generated using Minitab 17 software. So here the optimum desirability of 96.22% is achieved with flow rate of 460 gram per minute, standoff distance 4 mm, and travel speed 200 mm per minute, which predict the theta of 1.3059 and RA is 1.2313. This predicted value is validated with the fresh experiments, and 8.89 and 9.72 percentage of error is recorded for RA and theta. The value of this error is happened due to some measurement error and some vibrational things during the machining. But this is the favorable result because this error is less than 10%, means in this case where the 90% of the accuracy is achieved. At last, these two plans are proposed here. Number one is the TLBO, teaching learning based optimization techniques, and Jaya algorithm. So by applying such type of the algorithms, we can compare the results of existing system with Jaya and TLBO, because these are two the advanced algorithm which showed the best optimum solution. And by analyzing these algorithms, here it is useful to establish the novel results. Yes, so these are the main conclusions are drawn. So here it is reported that the travel speed is the most influencing factor, followed by flow rate and standoff distance. Here the models with more than 95% of the value showed the good relationship among the estimated and experimental data. Also, the optimum value of abrasive flow rate, travel speed, and standoff distance are useful for the machinists of AWGM. And such type of the study means use of and proposed study means Jaya and TLBO would be helpful for the shop floor industry for enhancing the productivity of Inconel 718. Based on these, here the two publications are already published. These are the references. Thank you.